In this video, we're going to take a look at two different tests for series. We're going to look at the divergence test and the integral test. These are going to be tests that will help us determine if a series converges or diverges or something like that. We're also going to look at two types of series. We're going to look at the harmonic series, which is a very specific series, and then we're going to look at a whole family of series called the P series, which will be very familiar to us because this is going to be very closely related to P integrals, which maybe makes sense because we're looking at an integral test. So there's going to be some sort of a connection here with series and integrals. We just have to discover it. So let's start things off by taking a look at the divergence test. This is what the divergence test says. There's two different statements. These two statements are equivalent. They're the same thing. So one of the ways of thinking about the divergence test is that if you have an infinite series and it converges, then we know that the limit of the terms has to have gone to zero. So let me say that again. If the series converges, the terms themselves have to go to zero. This doesn't mean they have to add up to zero. This just means they have to eventually end up being zero. Another way of saying this is that if the terms don't go to zero, if the limit of a sub n does not equal zero, then the related series has to diverge. So the only hope that we have of this series converging is if the terms themselves go to zero. This kind of equivalent statement here is called the contrapositive. You'll learn about that when you take a math logic class or a discrete math class or something that has like some proof stuff on here. Basically, it just means if you flip the implication and you change the negation on things, you get an equivalent statement. So if this converges, then the terms go to zero. If the terms don't go to zero, then the series doesn't converge. That's what we've got. Note that the divergence test never actually tells us if a series converges, or it tells us that a series converges. If we know that a series converges, then we know something about the terms. But this second statement is going to be the more helpful one. All it's going to do is tell us if a series diverges. Now, it's not going to tell us every case where the series diverges, just some of them. Here's the proof. We'll just kind of step through this really briefly. We're going to first consider some series, and it's got a sequence of partial sums. And we were told that if the series converges, then the sequence of partial sums has to converge. We know that already. We found that in our kind of very first discussion of series. So what we're going to assume here is that the limit... let me fix this for a second. All right, let's try this. There we go. That's better. I had to change a setting on my little writing tablet. Anyways, what this means is that this limit of the partial sums, we're going to say it just goes to some finite value s. S is just some real number. We're going to use it to represent the series. We're going to see if we can define the nth term of the sequence of sequence of terms, a sub n, using partial sums. So this is how we'll do it. We'll say a sub n is really equal to all the terms up to the nth term added up minus just the first n minus 1 terms. So you can say this is like a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n minus 2 plus a sub n minus 1 plus a sub n. And then this one is a sub 1 plus a sub 2 all the way up to a sub n minus 2 and a sub n minus 1, and we stop there. If you subtract these things, the only thing that's left over is this last term. But these are both just partial sums. So we'll call this s sub n, and we'll call this one here with the n minus 1, s sub n minus 1. So really we're just defining the nth term of our sequence, or of the sequence of terms, by partial sums. The reason we want to do this is that we want to show that if this series converges, this has to go to zero. So now we'll take a look at the limit of that nth term. We have an explicit formula. We'll just apply a limit as n goes to infinity. Now this is a little weird. We can split this up into two limits, essentially apply the limit to each of these terms and subtract them. And what you'll notice is that this limit we know. We were told that s sub n converges to some finite value s. So this thing goes to s. Now this one sometimes feels a little bit weird for students, so hang on. Notice that as n goes to infinity, n minus 1 is also going to go to infinity. What that means is that s sub n minus 1 is going to approach s as well. As n minus 1 goes to infinity, as n goes to infinity, n minus 1 goes to infinity. And so either way, we're looking at the kind of like limit of this sequence of partial sums. So what that means is that this limit that we had is really just s minus s, but those are the same value, and so the term has to go to 0. So if the series converges, meaning these partial sums actually do approach some real number value s, then we know that those terms in our sequence of terms has to go to 0. A couple of quick notes. Again, this theorem does not say anything about our series converging. A really quick and easy thing that people will mistake is they'll say if the terms go to 0, that means the series converges. That is not necessarily true. If they don't go to 0, we know that the series will diverge, but it's possible that the series could still diverge even if the terms go to 0. This is like every square is a rectangle, but not every rectangle is a square. Every series whose terms don't go to 0 diverges. But not every divergent series has terms that don't go to 0. There might be some where the terms go to 0. So we can't say anything if we find this limit of terms goes to 0. Again, we also commonly use the contrapositive statement. This means if the terms don't go to 0, that's what this little cross through the arrow thing means. The limit of that terms is not equal to 0. That's another way of saying this. Then we know that this does not converge. So here are some examples really quickly. Really quickly, if we just take a look at a limit of the nth term on this thing, we'll say that's n minus 5 over n plus 10. I'm just putting in n for this. Or some people will just do a limit as k goes to infinity, and they'll call this k minus 5 over k plus 10. Exactly the same thing. But either way, you should notice that this limit is just 1. Whether you're using L'Hopital's rule or looking at just the biggest terms on here, doesn't really matter. What we specifically care about, though, is that this does not go to 0, so the series diverges. Similarly, we can do this limit. I like to use n's because that's what our text uses, so I'm going to use that. Although it doesn't really matter, you could use k's. This one is infinity over infinity. We got to do this L'Hopital's rule, so maybe our good friend L'Hopital will come in and help us out. We're going to look at the limit as n goes to infinity of the derivative of the exponential over the derivative of the log, but that's really n e to the n, and that's infinity times infinity, which is infinity. So these terms actually just get really, 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 really big. It's impossible for us to add these things up and have it equal some finite number because not only do the terms not go to 0, they keep getting bigger and bigger and bigger, meaning really far down this series, you end up adding these huge values to your sum. Of course, your sum's not going to converge to anything. So the series diverges. Now, this is an interesting one, because as we look at the limit here of the terms, this goes to 0. So what's our conclusion? We don't know anything. Remember, the divergence test never tells us about convergence. So this, we say the divergence test fails. Now, that doesn't mean that it doesn't diverge. That just means we have no information about this thing. So that's how you apply the divergence test. Sometimes people will call this the nth term test or the kth term test because you look at the limit of the nth term as n goes to infinity and you see what it equals. This first series, you can say essentially what happens is really, really, really far down the series, you just end up adding 1 plus 1 plus 1 plus 1 plus 1. So of course the series is going to diverge. That's how the divergence test works. I want to look at that last series that we looked at, this one here, as k goes from 1 up to infinity of 1 over k. This is this very special series. It's called the Harmonic series. It's a super famous series. There's lots of good reasons why the Harmonic series is interesting, but I just want to jump into analyzing it a little bit. One of the cool things about the harmonic series is that it's very, very difficult to analyze it using partial sums. That's pretty much the only other way that we know how to deal with things so far. We have this divergence test now, which fails to tell us any information in this case. And so we might say, well, what about the limit as n goes to infinity of the partial sum? S sub n. So what I did is I just pulled up a little computer program. I wrote a really quick code to just find a whole bunch of partial sums. This is the first 100,000 partial sums of this. So at the very end, what we have here is the first 100,000 terms all added up. But here, this value here is the first 75,000 terms added up. This value here is the first 50,000 terms added up, etc., etc., etc. You can see that at the very beginning, we end up adding quite a bit, but eventually it does kind of look like it's maybe leveling off. So maybe it does look like the limit as n goes to infinity of this thing exists. Maybe. Couldn't there be like a horizontal asymptote that we're approaching? Well, instead of graphing it all, what I did is just found a whole bunch of values, and I just got approximations from places. So if you look at the first 10 to the 6, so this is the first million terms, it adds up to approximately 15, which is like up here, right? Our scale is in 12 and a halves, so 15 is up here. So like at a million, we end up getting to there. If you look at 10 to the 20, which is a 1 with 20 zeros afterwards, I do not know the name of that number. That first huge amount of terms adds up to around 47. And then if you look at the 10 to the 40, that's a 1 with 40 zeros afterwards. That is an astronomically large amount of terms. It adds up to approximately 93. The main thing is that it looks like this limit as n goes to infinity of S sub n doesn't exist. I'm going to put a question mark there, though, because we're not actually showing that. We're just approximating this limit for really, really, really big values of n and saying, like, oh, I don't know, it doesn't look like it's approaching anything specific. Maybe there's a cap at 150. I don't know. So this is what makes the harmonic series really, really difficult. So what we're going to do is prove this theorem here, that the harmonic series diverges, even though the limit of terms goes to 0. It's not the only series whose terms go to 0 and it diverges, but it's a really important one. If you look online, there's this really interesting paper written by Steve Kifowit, and I'm forgetting her first name, Stamps. They are professors at, I believe they're at Prairie State College down in Chicago Heights, and they wrote this really good paper that's called "The Harmonic Series Diverges Again and Again," and it's on Canvas. If you're in the Canvas course that I'm teaching, you can get a link to that, and it's got like, I forget how many proofs that the harmonic series diverges. It's a really cute little paper. It just goes through a whole bunch of historical proofs of the divergence of this series. They are all written at a level that Calc 2 students can understand. As long as you know a bit about sequences and series and a little bit of calculus, you can jump into this thing. So it's a really accessible paper. I'd encourage you to take a look at it. The proof that we're going to do is in this paper, although it's not my favorite proof. In this paper, there's some really cool ones, I think. But I'll leave them for you to look at, and maybe we can talk about them during office hours or something like that. So what we're going to do is just take a look at this proof. I forget which number this one is in the paper, but we're going to specifically look at the partial sum of this harmonic series, S sub n. And what I want to do is draw it. So let me draw a set of axes here. Oops, I want this. And I'm going to say that this here is, well, I don't actually want to say this. Never mind. I want to do this. Let me draw the terms themselves. How about that? That'll work. Okay. So, yeah. Let me go back. I'm sorry. Let me add that in here. I was right. I got all in my head for a second. 1, 2, 3, 4, blah, 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 n. All right, so our first term, these are just the terms themselves. So these are the a sub n's, not the partial sums. It's right here. Then our next one is at a half. And then our next one is at a third. It's like right there, maybe. And then we're at like a quarter, which is probably like right around there. And then eventually when n gets really, really big, we're going to have some small thing here. What I want to do, though, is draw something that I think will be helpful for us. If I draw this, this is the partial sum. Blah, blah, blah. Maybe I'll draw n minus 1 here. Oops. So we got a little bit bigger of 1 there. So I can actually draw a box in here yet still. What we'll notice is that this is the partial sum, this adding up area, right? We take the height of each term, multiply it by 1, and add them all together. So if we take a look at this area, and there's a whole bunch more boxes in here that we're missing, right? Whatever, blah, blah, blah. There we go. So if we take this area and we add up all the areas of the rectangles, we get the total partial sum that we're looking at. Now, what we'll notice is that this is a left Riemann approximation of the area under this curve. Now, this is our function 1 over x. And if we go back to Calc 1, when we set up these... Oh, I forgot my box here. There we go. I forgot the nth term that I had to add in. So, sorry, if we go back and add up all these areas, we're really going to get an area under our curve, and this is a left approximation, meaning this last box goes up to n plus 1, and so it's an area under our curve on this interval. Now, we can do a whole bunch of stuff now, and we can say, first off, notice L sub n is an over approximation. You maybe showed this in Calc 1, but at the very least we can just look at this and tell. All of these rectangles are above the curve. But you might remember that since your function is decreasing, that's the thing that's doing it. That's saying that the left sum is going to be an over approximation. So, since our first derivative is negative, the function is decreasing on the interval, we know that this left sum is an over approximation, and since the left sum was really the partial sum, we can say that that's overestimating this actual area from 1 up to n plus 1. Now, this is going up to n plus 1, remember, because we have to take the left sum, including this little subinterval at n. That's the x value that we use to approximate the rectangle from n to n plus 1. So that's why we're going all the way up to n plus 1. Now, if that's bigger, what we can do is figure out what this actually is. The antiderivative of this is the natural log. So this is just the natural log of x evaluated from 1 to n plus 1. And that's what we have right here. Natural log of 1 is equal to 0, though. So we just have this natural log of n plus 1. So if we want to figure out what the limit of this thing is, we know that it's bigger than the natural log, and so the limit of the partial sum is bigger than the limit of the log. Now, you might notice something. I know what this limit is. This is essentially like the natural log of infinity, which, if you remember, logs look like that, and they grow forever. So what that means is that this is infinity. So, since this limit is infinity, we know that our limit is bigger than infinity, which doesn't really make sense, so we'll say it's infinite. If the partial sums go off to infinity, that means they diverge. The sequence of partial sums diverges, and thus the harmonic series diverges. So this is, I think, a clever little proof because it gets to use this fact that we have about Riemann sums. And the reason that we do this proof here is not because it's the coolest proof that we have, but it's going to be helpful for us to try and notice a connection between series and integrals. So, the integral test. This is what the integral test says, that as long as f is continuous, positive, that just means that all of our function values are bigger than 0, and decreasing, so maybe you could think about this in terms of first derivative, right? For x greater than 0, then as long as we can match up our terms with a function output, so remember we're saying terms are really function outputs for these very specific inputs, just the positive integers. So that's why we only care about x greater than or equal to 1. So if you can match these up, then the series and the integral converge or diverge together. What that means is if one of them converges, so does the other. And if one of them diverges, so does the other. So notes. First off, if they converge, the value of the integral is very, very, very likely not the same as the value of the series. The only time that they would be the same is in like a trivial case maybe where you were looking at like a zero function or something like that, where everything just adds up to zero and there's zero area. There might be a couple of other weird little cases like that, but they're all going to be kind of like hacky cases. The very most case is that they're not going to be the same. And we can go back and think about why. It's going to be because of this picture. Our sum is different than our integral. We have like a discrete counting of finite number of, or an infinite number of things versus a continuous function where the values are going to be changing in between 1 and 2. Those are clearly going to end up being different. So they are likely not the same value. Mostly, we're going to be taking series and comparing them to integrals, since we're good at integrating. If instead we were really, really, really good at evaluating series and we were really bad at integrating, we might go the other way around. We might take some integral and we'd be looking at it and going like, oh man, I don't know what's going on. And so we'd connect it to a series. But for us, we're pretty good at integrating, not so good at figuring out what series are doing yet. So that's how we'll do things. The proof, we're going to be thinking about Riemann sums with decreasing functions. So I'm going to draw a decreasing function here. Let me put my axes in black. I'm just going to draw that like a 1 over x function just so we can look at that. And we're going to think about right Riemann sums. Oof. Here we go. We're going to think about a right Riemann sum, and you'll notice, oh yeah, on a decreasing function, your right Riemann sum underestimates. And we'll think about left Riemann sums. And oh yeah, with a decreasing function, your left Riemann sum is going to overestimate. So that's what we're looking at. It should make sense that we're only looking at decreasing functions, because if it wasn't decreasing, if it was positive and increasing, then the divergence test says the terms don't go to zero. And so we're done. Our series diverges. So it better makes sense that if we're looking at positive functions and positive terms in our series, they have to at least be decreasing. Because if they don't, then there's no way in hell they're going to end up going to zero. And so the divergence test will just take care of everything for us. Okay, let's prove the integral test. There's 2 proofs that we have to do here. Oh, what is this? That's supposed to be an infinity. I probably typed in int instead of infinity or something like that. So here, let me fix that. I'm going to give myself a white marker, cover up that integral sign, look at me go. And now I will add an infinity sign. There we go. So we're going to say if the integral converges, then we have to prove that the series converges as well. And then we'll do the opposite direction. We'll do another proof where we assume that the series converges, and we'll show that the integral has to as well. So let's start in this direction. I got to change that again. Oh boy. I probably just copy-pasted or whatever. All right, there, good enough. And let's add an infinity. All right, perfect. Okay, so that's what we're going to show. So first, suppose that this integral actually does converge. We're going to try and show that the series converges as well. So if it converges, let's just call it equal to some number I, just some real number. We're going to consider partial sums here. This better makes sense. A1 minus A1 is nothing. It's 0. So we're really just adding something and subtracting. But we're going to notice that we can write this as a series from k equals 1 up to n. That's what the partial sum is. Minus a sub 1. This is really a series of k equals 2 up to n of a sub k. So that's something that might be interesting. So that's what I'm going to replace here. Hey, notice this is a right Riemann sum. Let me draw it and we'll make sure. So here comes our function. We're going to start at 2, 3. I'll put 1 in there as well. 4, blah, 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 up to n. And if we look at adding these things up, I'll just put them all in here. We've got some decreasing function. Then what we're really doing is adding up just these ones. And that is a right Riemann sum if your curve looks like this. All right, so this is just a right Riemann sum approximation. Notice that we do go up to the nth one, so it's r sub n. And in this case, we said that the right Riemann sum is going to under-approximate things. So if that's an under approximation, that means the integral is actually bigger than this thing. And so the actual integral, we're going to swap it out because it's bigger, and we use this sign now. So for our series, it's less than a sub 1 plus this integral. What we'll do now is notice that you can just take n and bump it up to infinity, because what that means is that we're adding more area. We're going a little bit farther on our function, and so it's just going to get even bigger. And since we're just stringing together inequalities, we'll just say, okay, even bigger yet is this where n goes to infinity. And again, that's because of this ordering of these two integrals. But we know what this integral is. We said that that converges. It's equal to I. So our series is less than some value. That means that our partial sum, s sub n, is less than a sub 1 plus I. And so that means it's bounded above. We know that the sequence of partial sums is monotonic. It's increasing because all the terms are positive. So that means when you add more and more terms, your sum gets bigger. So the sequence of partial sums is monotonic, and we've just shown that it's bounded. We had a theorem earlier that says, hey, any sequence that's monotonic and bounded, that converges. So bang, we know the sequence of partial sums has to converge, and thus so does the series. End of proof for that first direction. Let's take a look at the second direction. We're going to suppose that the series converges, and we're essentially going to recreate things, but instead of using partial sums, we'll use partial integrals. So we'll say if the series converges is just equal to some number s, we're going to go ahead and set things up looking at a partial integral. We're going to say this is less than this thing, because that's a left Riemann sum. I'll let you draw it, but we've got this decreasing function, and so we know that the left Riemann sum over approximates things, so it's actually bigger than the integral. Oops, I forgot a differential here. dx. So our integral is a little bit less than whatever this left Riemann sum is. And now again, we'll switch n minus 1 to infinity. We're just adding more and more terms. Since all of our terms are bigger than 0, it's still smaller yet, but we know that this series converges because that's what we're assuming, and so it's equal to s. So what we have is this integral from 1 up to n of f of x dx is bounded above by whatever the series is. Now what we're going to do is use that monotonic bounded convergence thing. For every n, we have this inequality. That means the sequence of these things is bounded. We know it's monotonic because as you add more x values here, as n gets bigger, we're adding more area, so it's increasing. We also know that it's bounded by this. And so we know that this thing has to converge, this sequence here. Now, if this sequence converges, that means the limit exists, right? And so, hey, wait, this limit, that's what this integral is. So we know this integral converges. Done. If the series converges, so does the integral. So what the integral test says is you can just connect these things. So let's take a look at some examples of why this is really helpful. In all three of these do not look like nice integral or series, sorry. But if we imagined these as integrals instead, and we say, well, let's think of this as the integral from 1 to infinity of x over x squared plus 1 dx, we might have some intuition about how to deal with this. Doesn't this look like we could just do a u sub? U is equal to x squared plus 1. Du is 2x dx. So we've got an integral, half the integral from 2 to infinity, because remember I'm taking these x values, plugging them in here for x, and getting new u values, of 1 over u du. That is a p integral. It diverges. You could say the antiderivative is the log, right? And when you throw this infinity into that logarithm, it's going to go off to infinity. So that means this series diverges. Notice I didn't figure out what this integral converges to because I don't really care. It doesn't matter to me what it converges to because the series is going to converge to something different, but it will converge. In this one, we'll take a look at the integral from 3 to infinity of 1 over the square root of 2x minus 5 dx. And hey, doesn't this look like another u substitution? I'll let you set this one up and see what happens. And for this one, we're going to look at an integral from 0 to infinity of 1 over x squared plus 4 dx. And I don't want to give you any hints on how this one's going to go, but see if you can figure these ones out. Go. Pause the video and see what you got. All right, so this is what we've got for our integrals. I just went ahead on this second one and did a u substitution on here again, and we get this 1 over u to the half. Oh my gosh, I forgot my differential again. I'm tripping. There we go. We've got this 1 over u to the half du. This is a p integral. P is small, and so you might remember that we said that means that this is going to diverge. You could anti-differentiate this if you want and use limits and see what's going on, but all we care about is this thing diverges. And so we know this series diverges as well. In this last one here, I just used an inverse tangent on this. You can do some other things as well, but the inverse tangent will work. And I said, all right, the antiderivative of this is 1/2 inverse tangent of x over 2. I'm going to evaluate it from 0 to t using this limit as t goes to infinity. So I've got this half limit of as t goes to infinity of the inverse tangent of t over 2. This is really inverse tangent of infinity. The end behavior of inverse tangent, you might remember, is at pi over 2. And so I know this limit's going to be pi over 2. This one is 0 because there's this point right here. And so I've got half of pi over 2, which is pi over 4. But all I really care about is that this means our series converges. We don't know what it converges to. Not pi over 4, but it converges to something. There is some real number. So all we know is that it converges. Hopefully those 3 examples are pretty helpful. The last thing that we want to do in this video is to just say, wait a second, the integral test says that integrals in series acts the same way. So here, p series. Notice it's the same criteria for a p integral. A series that's 1 over k to the p, if p is bigger than 1, then we know it converges. And if p is between 0 and 1, then we know it diverges. Meaning we can just take a look at a whole bunch of examples that are really easy if they're set up right. 1 over k squared, I don't have to think very hard and say this converges because p is 2. Now, we can change the index a bit. And I can say this thing converges as well. P is 3/2. That's bigger than 1. So this is going to converge. It doesn't matter if I don't start at 1 because the part of the series that determines whether it's going to converge or diverge is the very, quote, end of the series. It's all the last terms. It's not the first ones. And so we know that this thing converges as well. Cool. That's all we've got. So the main 2 things here, divergence test, if the terms don't go to 0, your series diverges. And the integral test, series and their corresponding integrals act the same. They converge and diverge together. That's really helpful when things look like they could be set up where we could do some integration. If it looks like some nice u substitution or like an inverse tangent or an inverse sine or something that we might know a little bit about as our antiderivatives, then we'll go ahead and convert things over to integrals and check them out. But that also unlocks everything that we know about integrals, which includes those p integrals. So here we go, p series. That's what we've got for these 2 tests. Good luck, everybody. Jump into some problems, give them a try.